It's still a PPT.
No, no, the PDF that you opened was the one.
For this one?
Yeah, yeah,
Okay.
this one.
Okay. Okay, what's that? I see.
Yes, okay. You need to click on this. And control click it. Then this is working, right?
Yeah, it's working. Next slide. Yeah. This mic is not working.
Yeah.
Oh, no, it's working.
Just give them one couple of more minutes.
Yeah. हाँ, पोडियम से ज़्यादा दूर ना जाए, पोडियम से ज़्यादा दूर ना जाए। अच्छा, ये पोडियम है। हाँ, बोल रहे हैं। ओके।
और ऊपर वो पॉइंट का है वो दिखाई।
कितना ऊपर? आधा से यार वो स्पीकर है ना, उसकी लाइन से आगे लगा। This is the pointer. Yeah.
Can you hide this?
I think you have to move around.
ये इसको वो कर सकते हैं क्या कर सकते हैं? ये छोड़ चला गया क्या करना है कुछ नहीं ये अपने से चला
वो अपने ऊपर चला गया।
ठीक है। Okay, good afternoon, everyone. It's an absolute pleasure for me to introduce our keynote speaker, Professor Caragiannis. So Dr. Caragiannis is a professor of computer science at the Aarhus University, where he heads the computational complexity and the game theory group. Before Aarhus, Professor Caragiannis was a faculty member at the University of Patras. Professor Caragiannis has made influential contributions at the intersection of computer science and mathematical economics. He has written over 180 papers on topics such as algorithmic game theory, approximation algorithms, computation social choice, and their applications to domains such as the kidney exchange program. One of his many influential works is his Kalai Prize-winning paper that establishes the harmony between fairness and economic efficiency. It's a great piece of work that leads to many sleepless nights. It formulates this one of the central open problems in discrete fair division called the EFX conjecture. It's a beautiful problem. So please do ask about him, ask him about the problem or a coffee break. So indeed, Professor Caragiannis' work has really challenged, inspired, and enlightened us. And I'm sure that today's talk will substantiate this observation in the context of social choice, in the context of distortion in social choice. And so please join me in welcoming Professor Caragiannis for what is guaranteed to be a very interesting talk.
Thank you. Thanks a lot, Siddharth, for the nice introduction. Thanks to the organizers for inviting me. A big thanks because they also solved or helped solve some visa issues that seem really impossible to solve at some point. So today I'll tell you two stories about distortion in social choice. I'll give some background at the beginning and I'll spend more time on the first one and then I'll tell you about the second one. So these are two stories on recent. These two stories are based on recent work on distortion of impartial cultural electorates. I'll explain what this is. This is joint work with my PhD student Carl Coach. And the second one is on the distortion of sortition. So this is joint work with Evi Micha and Ioannis. So let's start with the first story. So the first story is about distortion of voting. So if you're working in the area and social choice, then you know what this picture in the upper right corner is. This is the picture in the cover of the Handbook of Computational Social Choice, and it was published a few years ago. It's now obsolete, but it reports on early work on voting, matching, square division, and other stuff. So since then, there is a lot of work, including the work on distortion, part of which I'm going to present today. So in voting, we have the voters, or agents, as we usually like to call them, and we have alternatives or candidates. So in our example, the voters are, let's say, scientists in a research institute, and the alternatives are different equipment that the institute would like to buy, but has money, has available budget for just one purchase. So the alternatives here are the chemistry lab, a magnet, a telescope, a microscope, or a supercomputer. And the voting rules are really simple ways for decision making, taking into account preferences. And of course, voting is important for democracy and is and has mainly been considered by the social choice community as the way to run elections. But so in the social choice, a large part focuses on the study of axiomatic properties of voting rules, and which, in other words, which of them are good for use in a government election, which are not that great. There is a smaller part of the computational social choice community who focus on the amenability of voting rules as ways to compute efficient outcomes. And in a sense, as single ways to optimize decisions. So I'm a big fan of this second approach, and what I'm going to present today is belongs in this capítulo. So in voting rules, we have agents. So these 5 guys over there, and each agent submits a ranking of the alternatives. So that's the preference of the agent. So for example, the first agent has the chemistry lab in the top of her preference, then the magnet, and so on, then the supercomputer is last. So the voting rule will take the preferences of all agents, or the profile of rankings of the alternatives, and will output a single winning alternative. So there are, of course, variations. There are voting rules which report committees of alternatives or sets of alternatives, voting rules that report rankings of alternatives. So let's stick with voting rules that return a single winning alternative. Okay, and this single winning alternative has been selected using a voting rule called plurality, which ignores completely the ranking of the candidates, just looks at the top position and selects the alternative that has the highest number of appearances in the top position. And according to this plurality rule, the chemistry lab will be the winner for this profile. If we use a rule called Borda, which gives many points on the alternatives at the top position, a bit fewer points for the alternatives in second position, and so on, then we'll have the magnet as the winner here. So the magnet appears 2 times in the top, 2 times in the second position. and so on. And if we use the details of the border rule, then we can see that this is the winner here. And there are other rules like the veto rule, which looks at the last position in the rankings of the voters and returns as winner the alternative that has the minimum number, the smaller number of it. So according to this rule, the tell us what will be. So we have different rules for different selections of the winning alternatives. So here we would like to evaluate the voting rules according to their efficiency, according to how good decisions we can take with these rules. And to do so, we assume that the agents, the voters, have values for the alternatives, and the rankings they submit to the voting rule are just consistent with these values. So in this example here, the first voter has almost the same values for all alternatives. There are small differences in the ranking of the ranking submitted to the voting rule here just reflects the small differences. So other agents, the second one, for example, has two alternatives with very high values, again, different, and then three alternatives with almost zero value, and the ranking represents this order of values. Still, the voting rule has no idea about this information, about the values. It takes as input the rankings and has to decide the alternative using looking on there. Okay, and then the quality of an outcome is what we call the social welfare. So the social welfare is just the sum of the values. The social welfare of an alternative is just the sum of the values an alternative has, and we'd like to select the alternative of highest social welfare. So for example, here, these are the numbers, the total values of the 5 alternatives, and this is what these are the alternatives returned by the 3 rules. It turns out that the optimal alternative, the alternative that has the highest social welfare, is the supercomputer, which if we go back and see the example, there's probably no reasonable voting rule that can identify this alternative. So we will be happy with a good approximation of the optimal alternative, and in that case, we'll say that the voting rule is pretty good. So some notation. I'll try to keep the presentation light and just give the main ideas, no details, but it's necessary to give some formal definitions. So N is the number of agents, M is the number of alternatives. So agent I has a non-negative valuation V sub I of A for alternative A. We use the notion of the valuation profile V, that is the matrix that has all values of agents for alternatives. And we use this notation for the ranking of agent I, and this is consistent to the valuations that the agent I has for the alternatives, in the sense that agent I prefers alternative A to alternative B in the case where the value he has for alternative A is at least as high as the value he has for alternative B. Then the ranking profile, capital P, is just a vector with all these rankings, and we use this notation to denote that the ranking profile is consistent with the evaluation profile. Then we have the social welfare of alternative A for voters with this valuation profile, and this is defined as the sum of all voters of the values the voters have for alternative A. And among all alternatives, the one that has the maximum social welfare is the optimal alternative, and we use this as W star to denote this optimal, this maximum possible social welfare. Okay, and then we can define this distortion, the notion of distortion. So we consider voting rules. We view voting rules as functions. Function F that takes us into the ranking profile has no idea about the voting rule, has no idea about values. It just returns a single alternative A. And then the distortion of this voting rule is defined as follows: is the maximum over all valuation profiles, the maximum overall consistent ranking profiles to these valuations. We may have ties and we may have different ways to resolve the ties, and that's why we may have different profiles here. We take the worst possible, and then this ratio is the ratio of the maximum possible social welfare among the alternatives in the valuation profile over the social welfare that of the alternative that is returned by the voting rule. So essentially, so if you have worked on approximation algorithms, price of anarchy, this kind of things, then this is a definition that is very close to those. So essentially, the distortion tells us how far from optimality the outcome of a voting rule can be. Okay, and the notion was introduced in 2006 by Caragiannis and Shine. Later, we had this paper where we answered several, we presented bounds for several voting rules. Some of the open problems were recently solved in this paper here, and this paper by Anselevich et al. It's a survey in Sky 2021 with results on distortion until then. So there are some recent developments that are not there, but this survey is a very starting point for somebody who wants to see what is the current working theory. Yes. Yes.
So somehow there's a take into account the fact that these values assigned need to be normalized. Like I might assign a higher value to one or alternative, to all my alternatives.
Yes. So this is okay. So the values of the alternative reflect the fact that the scientists that we saw, the voters, believe that the value would be the funding that the group, the institute can attract if they have the particular agreement. And then this number can be high, can be low. In our examples, we have normalization, so the values sum up to 1. In general, we're interested in that's general valuation profiles. Right, but there are limitations. Say a few things about it. Sure.
Value for each agent sums up to 1 for all the
Not necessarily. So this is the case in our results. This is the case in some of the in previous work, but yeah. Okay. Yeah, just to give a flavor of the results of distortion. So we proved in this 2015 paper that plurality has distortion n squared, so n is the number of alternatives, and this is optimal among deterministic voting rules. The best possible distortion among randomized rules is square root of n. We have proven some the lower bound and some slightly worse upper bound that has an low scale and term, which was recently improved to the type bound by Ioannis et al. And in all these results, the assumption is that we have unit sum valuation. There are also some related work assuming unit range of values. So unit range means that each agent has a value of 1 for some alternative, a value for 0 for some other alternative, and values in between for the rest of alternatives. And yeah, so assumptions of this kind are necessary if we want to have meaningful results for deterministic voting rules, for example. So if we don't have these restrictions, then one of the voters may have a huge value. I guess that's the example that you had in mind. All other values are small. Then the voting rule will not be, I mean, has no way, if it is deterministic, has no way to distinguish between, has no way to see hidden value behind the rankings, and inevitably the distortion will be infinite. So previous work restricted consider restrictions of valuation to this unit sum. And then there was, I mean, starting from this difficulty, there was this nice paper by previous Caragiannis and Budouris some years ago, and they assumed that in addition to the ranking profile, the voting rule, or now better because it's more sophisticated than a voting rule, can make a small number of valid queries to each agent. And the query can have different types of the query. They mainly consider the query today is of the following kind. So it's the query is to some agent. So agent I, what is your value for alternative A? And then the agent will report correctly, so there is no strategic issue here, the underlying value of, let's say, 0.2. And there are many results of that paper. So my favorite one is that you can achieve constant distortion using log squared and queries per agent. And the important characteristic is that there is no restriction on the valuation here. So if some agent has high valuations making queries, this log square and queries can identify whether some agent is more important than others in their valuation. Okay, so this is the model. This is the query model we'd like to consider, and in this work with my student Carl First, we consider the following variation. We don't assume that the underlying values are arbitrary, but instead we assume that each agent draws a value for each alternative according to this probability distribution capital F, IID. So the assignment of value for each alternative is independent from any other. And yeah, so essentially then we have a random valuation, a random value per agent alternative and a random valuation profile. And then the consistent ranking profile POV is obtained in the obvious way from the valuation profile. We breaking ties among alternatives uniformly at random. So if we have a distribution that does not contain, that does not have probability mass anywhere, then we know that the certainty will not have to resolve ties. It will have to resolve uniformly at random. And then we define the average distortion of an as follows. So the average distortion of mechanism F for profiles that are produced according to this probability distribution calculation is this ratio. So the numerator has the expected optimal social welfare, and the denominator has the expected social welfare of the alternative returned by the mechanism. So now the mechanism takes a simple vector profile, a ranking profile, as well as a limited number of queries per agent. So that's why we don't have just the profile as argument here, but also this valuation profile. Okay, so this is our goal. We'd like to design voting rules or mechanisms that have low average distortion with a small number of agent queries, if possible. So essentially, the mechanism takes the ranking profile for free and can make a small number of additional queries. And the simplest, and we started from the simplest assumption. So let's assume that we have a binary distribution, and with probability P, the distribution returns 1, with probability 1 minus P returns 0. And here is an example when the when the values are grown with probability 50% to be 1, probability 50% to be 0. And believe me that this is a random valuation profile that follows this rule, and this is the random way to resolve the ties whenever it happens. So essentially what the voting rule will see is a random profile. In the social choice, the study of random profiles, these random profiles are known as following the impartial culture assumption. They have proved to be useful for some studies. They have received criticism as non-realistic, but that's a good starting point for what we're trying to do. Okay, and the first result is a bit disappointing. So the average distortion, if we don't make queries, even for this simple case, it can be bad. So how bad? So essentially we prove that it can be as bad as picking a fixed or a random alternative. If we pick a random alternative, then we have probability 1/n to pick the alternative that has the highest social welfare. So this gives us a distortion. So this argument here tells us that we shouldn't hope for something better. So if we use a binary distribution with very small probability, so how small? So sufficiently small so that the numerator in the average distortion definition is a constant. It's 1, let's say. Then with very high probability, we have that we'll see 1, maybe 2 ones in the whole profile, and these ones will be somewhere in the top positions of some of the agents. And then what we can show is that there is no way to distinguish between voters who have a value of 0 for the top alternatives with voters that have a value of 1 for the top alternative, and there's no way to identify where this single one goes. There are a few details in the formal argument to make this work, but essentially we get this omega of n distortion if we don't use any query. And then we have the following. So making queries is really important if we want to improve things. And and then we can make our life as easy as possible, assuming that we know the probability distribution. So let's assume that we know P, and let's assume that we query the value agent of this agent for the alternative telescope, and we get a value of 1. Then we know for free that the value for the other two alternatives is also 1. If we got a value of 0 as something, then we have the information that the values for the alternatives ranked low is also. Okay, so we're in a single case where the answer to the query gives us more information than just a single value, and we'll use it to define this notion of implied social welfare. So we'll try to define a mechanism that uses just a single query per agent, and we'll use the notion of the implied social welfare to decide which alternative the mechanism will return. Okay, so what is the implied social welfare of an alternative? Is the number of agents who return 1 to the query and ranked the alternative either at the position query or at the higher position. So here is an example. So we have this underlying value. So we have this ranking profile, and we see here that so we query the second position, values, and immediately we know that for example, in this fourth agent, this 0 tells us that this the four of the alternatives have a value. We have an idea about the microscope. So we forget about this agent. We also forget about the positions. I mean, the agents in which the query returned 1, we are not sure about the values that the agent has for this alternative at the bottom of the ranking, so we forget this too. And then implied social welfare is the score the alternative number of appearance the alternatives have in these positions here. And if we, in this example, we see that the supercomputer is the alternative with the highest implied social welfare, will be the could be the winner of a mechanism that uses this principle. And here is the mechanism, we call it mean. So it takes us into the profile P, consistent with a random agent alternative values drawn from a binary probability distribution with no probability parameter. And then, since we know the probability parameter, we query each agent at this position where we expect the ones to, the ones will stop and zeros will start. And and then we return the alternative the highest implied social welfare, and that's the first mechanism we start. So what we can show with this mechanism is it has constant average distortion. So the setting is very simple, right? I mean, a binary probability distribution, we know the probability P, still proving this constant average distortion was really challenging. So we had to consider three different cases. A case for small probability P, so this is essentially the case in the lower bound of showed before, and intermediate values for the probability and large values for this probability. We have different techniques to prove the bound for each case. So in these two cases, the bound is small, it's something like 2 or even below. For this case here, the bound we get is 27. And we strongly believe that that's, that the right answer is much closer to 2 than 27. Okay, so our observation here is that if the probability is large, the high concentration bounds, we know more or less that the social welfare of the alternatives will be sharply concentrated around an expectation. And if they're sharply concentrated around the expectation, then we can show that if the probability is sufficiently large, then even without queries, then all alternatives will have a social welfare that is, that is only a constant factor. So there's nothing to prove if the P is very large. So this large case here includes a large range of probability values in which these arguments cannot be applied. Actually, we don't even use these arguments to. So the arguments we use in the large P regime are, do not make any use of Chernoff bounds or stuff like that. Okay, and then once we have this mechanism, we can use it to solve the case of general distributions. So how can we do this? So yeah, just a simple idea is to use K thresholds and select one of these K thresholds uniformly at random, and then interpret the values that, and then query. And then interpret values that are above the threshold as ones and values that are below the threshold as 0. And if we, and with this interpretation, we can just apply mechanisms. So we have some thresholds, a number of thresholds, we see how many. We select one of them uniformly at random, run mechanism mean, interpreting the values that are above the threshold as 1 and the values below the threshold as 0. Okay, the probability we need to use is this probability that a value returned by the distribution is above the threshold. And so if we use this idea, then we can show that we can set K appropriately so that we get a mechanism that has distortion logarithm of n plus the logarithm of the ratio of the variance over mean square of the square of the mean of the distribution. And for most distributions, this just gives us a logarithm of n. There's some extreme values of the parameters of some distributions like airlines, for example, that give a higher bound, but these are very, very low. And the important characteristic of this mechanism is that it makes exactly one query. So with just a single query, we have a logarithmic distortion for general probability, for most general, for most probability distributions. We have some more results in that paper. So until now, I presented mechanisms for this model of random values, but actually the ideas can be used to design randomized mechanisms for the case where the underlying values are arbitrary. And in this way, we obtain a randomized mechanism with the worst case distortion logarithmic using logarithmic weighted operation. And we also have lower bounds for the case of deterministic mechanism. So we have this lower bound of log m log m queries per agent are necessary to get constant worst case distortion. So this has to be compared with the log square upper bound in the previous page. And there are many open problems. So the most important among them is whether we can achieve constant distortion for every probability distribution using a constant number of queries, one query possible. And once we understand once we have a good idea of distribution of the case of known probability distribution, we should answer the important question of unknown probability distribution. So sometimes, since we can make queries and learn the distribution, it seems that that results in this direction would be possible. So for the mechanism we have, we're missing something. So the bounds on the parameter P that we can learn and the cases for parameter P we have in the analysis are not exactly, so this learning that the ways we have to learn the value of P are not enough to recover the results in the case that the distribution is unknown. And in the case of worst of arbitrary underlying values, we like to understand the problem and get the type bound on the number of queries, we get constant worst case distortion. So this was the end of the first story. And I'll continue with the second one, which is the metric, which is about the metric distortion of sortition. So sortition is the practice of selecting a citizens' assembly or a panel to decide among alternatives for a given issue. So this is used in some municipalities and in order to make decisions about some issue, let's say decisions related to climate change, they select a panel of citizens, and this panel has to make this decision. So usually these decisions are not binding, but the practice of sortition has been used in several cases just to increase the awareness of the general public for the issue. And so this is the logo of Sortition Foundations, which an advocate for the use of sortition in modern society. And the desired property that has been studied in the literature is fairness. Fairness is the selection of citizens so that they're representative of the different characteristics in the population, among the citizens. So the first paper is a recent Nature paper by the group of Ioannis. The last paper presents an algorithm which we also use in some of our research. Okay, instead of studying the fairness of sortition, we focus on efficiency of the decisions that the panel can make. And this efficiency is constrained by the fact that the panel should be selected in a fair way. We use a variant of sortition, and the results I'm going to present are in this recent single paper with every papers. Okay, some notation. So we have citizens and we have alternatives, and all of them are points in the metric space. And okay, so essentially we assume that the agents have costs for the alternatives, and ideally we would like to select an alternative that is close to as many points as possible, or that the total distance of this alternative to all agents is as small as possible. Yeah, so panels are just subsets of agents, and we reserve K for the size of the panel, and then the social cost of the panel P for alternative A is we use this notation for it, and is defined as the sum over all agents in the panel of the distance to the alternative. And yeah, so if we are talking about the whole population, then we drop P from notation, and there is an optimal alternative, which is, I mean, from this capital A alternatives, which is just the alternative that has the minimum social welfare, the minimum sum of distance from each agent in the population. And every time that a panel has to decide from an alternative, we assume that the members of the panel can deliberate sufficiently well, and they select the best alternative for them. So essentially, the alternative of minimum social cost for the panel. So let me give you an example. So here is an example with 11 citizens. These are points in this space, and we have 4 alternatives. So a museum, a library, a school, and a church. And if we see the distances of the alternatives from all citizens, then we'll see that this is the alternative that would be selected. Instead, we don't want to have all the citizens deliberate, because this is not scalable. And instead, sortition picks a small sample of citizens to do the job. And now for these 5 citizens, it seems that this is the alternative that minimizes the distance, and if they deliberate, they would return this alternative as the decision of the panel. So now the question is, how good is the alternative that is the outcome of the deliberation among the members of the panel compared to the alternative that the whole population likes? And we can define again notion of the distortion in this way. So we assume that the way the panel is selected is randomized, and each member, so this captures fairness, each member is selected with probability K over K is the number, the size of the panel, over N, which is the number of agents in the population. And then the ex-ante metric distortion is just this ratio. So in the denominator, we have the optimal social cost for the whole population, and in the numerator, we have the expected social cost for the whole population of the alternative returned by the panel. And yeah, so this is an expected value, which can be very bad. So we would like to study the exposed distortion as well, where instead of the expectation, we have the maximum value this random variable here can take. So this is a worst case. So this exposed metric distortion is a worst case. Okay, and yeah, so this is the fairness criterion. So each agent is selecting the panel probability K over N, and one example is that the algorithm that selects uniformly at random one of the sets of size K of members of the population. And then we have this theorem that says that if K is has size log n over the square of epsilon, then we get ex-ante metric distortion 1 plus epsilon, or any set of the alternatives in the metric space. Which means that selecting randomly a subset of the agents, no matter where the alternative points will appear, as long as we have m of them, then we can have then the expectation, the ex-ante distortion we get for this random panel will be 1 plus epsilon times the optimal. So this is sort of a dimensionality reduction result. So we have these parameters, and we can, for panels of this size, we can accommodate issues with M alternative, with a loss, with a distortion 1 plus epsilon. So what is the problem? So the analysis has to take care of minor correlations, but we can do so using a variation of isomers inequality. I think specifically we use Surfling's lemma in the proofs. And the drawback is that the exposed distortion can be very, very high. With some small probability, we may select a panel of a panel that is at the edge of the population, and then with this probability, the exposed distortion would be high. So we would like to do something about this, and so what we do is we exploit a simple algorithm called fair critic capture, proposed by Ioannis and Mika in a paper from last year. This is a variant of a well-known algorithm for clustering by Chen et al. And the algorithm works as follows. So it starts blowing bolts centered at its agent until some of them covers n over k new agents. So if this is the case, then we select uniformly at random one of these n over k agents, and this is our next member for the panel. We do this, we repeat this k times. So here is an example. So I've rounded the number of agents to 12. We want to select a committee of size k. So we start drawing circles centered at each agent, and we realize that the first such circle that covers n over k, so 4 agents is this one. We select uniformly at random one of these guys to be the first member of the panel. So here's the first member of the panel. Then we continue drawing the circles from that point, and we realize that the second circle that covers n over k citizens is this one. Select uniformly at random, and then we complete by selecting uniformly at random among the remaining citizens. So this is a fair critic capture mechanism, and what we can show now is first that the mechanism is fair, and to see why it is fair, all we have to see is that the way the algorithm works, the sets of citizens among which we select the next member of the panel is fixed. So it's decided deterministically, and then proving fairness is actually trivial. So our result is that if we select this number of members of the panel, so the logarithm of the number of alternatives m over epsilon cubed, then fair critic capture has ex-ante strict distortion 1 plus epsilon and only constant exposed distortion. So again, for every set of alternatives that we'll have to select among, then using this random panel, we can have an expected ex-ante distortion 1 plus epsilon, and we'll never see a distortion higher than this number, 127. So that's the drawback of the mechanism. It's large. We'd like something better than this. So of course it's not tight. I mean, there is a hope that this number can. I mean that this particular algorithm has better performance in terms of the exposed distortion, but also there is an epsilon factor it seems we lose here. So it might be the case that the same mechanism gets a much better result. So these are the main open problems. So we'd like to get a better deterministic, a better exposed distortion. And here we have a lower bound for deterministic selection algorithms, which is actually a lower bound for exposed distortion. The lower bound is as small as 3. So interestingly, fairness gives us, I mean, even if we are not correct with it, we don't select correctly the size of the panel, then we always get a distortion of 3 or better. And we can also show that the panel size of log m over epsilon squared is not enough for ex-ante distortion. The question is whether we can combine the two results and get a best of both worlds results like the one that the fair greedy capture algorithm almost achieves. So ideally, would like log m over epsilon square ex ante distortion with log m over epsilon square queries per agent to get 1 plus epsilon ex ante distortion and as close to 5 as possible ex post distortion. Yeah, and that's the end of the second story. I'll stop here. Thank you very much.
Actually, is the input to the selection algorithms, which is what, where exactly the agents lie in the metric space.
Exactly, yeah.
So, and do we know anything about the alternatives or do they know?
No, the alternatives will come later.
Okay.
So you mentioned that there is a common probability distribution. And that all the values of operations are chosen as sort of picked from the distribution kind of something. But is that kind of I mean, is that yeah. Is that like somewhere seen in real life or
Values of random have some randomness. Of course, they're not isolated. They're not even relation that they're independent. Assuming that the electrons are the same probability in this algorithm. That's the first step. So there are several next steps. So, for example, each agent has a different, so there is a different probability distribution per algorithm. I guess this case is easier than what we studied. And we could, again, we cover the constant distortion bound. The most important case is if each agent has a different probability distribution for all alternatives. And in that case, our technique or some of our techniques do not work because one of the arguments we use is the following. So if we take a block of agents, I mean, two blocks of agents of the same size, the distribution of the best alternative there is essentially the same. So this is crucial in our analysis. If we deviate from the assumption of the same distribution, then we don't have this propagation. Right? Yeah, no, I have one more question.
Can you repeat the question if you didn't hear?
yeah, one more question. You mentioned that there are some situations or some kind of algorithms where you can make login number of queries and get a constant distortion. Now, my question is, what does the login number of queries look like? Do I, in a coding system, do I ask a person and then ask another person and then go back to the same person? How does this?
That's a good question. So if we query the top, so we want to solve the problem for agents who have completely different valuations for the items, not necessarily summing up one. So we can query the top position of an alternative of the ranking of an agent and have an idea of how, what kind of values the agent assigns to the alternative. And then it turns out that the values that are important to have a good distortion are those that are from this value that the top alternative this agent gives to the value, to the alternative that gets this value of n. To find this alternative, we can do some binary search. And then we need another binary search to realize what is. So first, we have n alternatives, so one binary search gives us a lot of n factor, and another binary search will give us a particular value that the last alternative. or another finance system will give us approximations of the values that they have. So that's how we get the log m square distortion. So the algorithm is very nice to get. Yeah. Which means that it's very, yeah, it's really, I mean, it gives you the feeling that we're very close. A slightly different idea will give us the time bounds. But after this optimism, then one can realize the problem is really.
Thus, how much of this extends to when agents are strategic? Like, why will they might have the evaluations, hidden evaluations, but once they know the voting rule, why will they be honest about it? Why will they
Yeah, so in voting, there is this Gibbard-Satterwhite theorem that tells us essentially that only dictatorship is truthful. And this is disappointing enough so that we don't actually try to find simpler models, restricted models where we can try to prove this kind of statements. But there are some results. So for example, if we know that the valuations are single peaked, then interesting non-dictatorial rules work. It's not clear how this can be combined with the independence assumption we have here, but I guess the short answer is that these variations of the model are important to consider and try to find the restricted variation that is restricted enough so that strategy proof or truthful mechanisms exist.
So in the committee selection question,
Yeah.
So in the committee selection question, are there some like price selecting variants also known? So like so you don't necessarily need a committee of FSTTCS, but you can have to get all P of A and then you get some efficiency. So then you have to maximize like something like a combination of the price you pay and the
Sorry, can you repeat that? I think I missed the.
So what I'm saying is this committee selection problem, like here we have something like we have to open some K, like we have set a committee of K members, and then you get some efficiency out of it, So we can have a meeting where something like you with the number of members you need to select is a variable, but like you have to pay some price. So let's say you have to open I member plan.
Yeah, actually, I haven't thought about this. So there is this participatory budgeting problem in voting. I mean, instead of selecting a committee of fixed size, in participatory budgeting, the municipality has a fixed budget, and this budget can be used to implement several available projects, and then the number is not fixed. So this seems close to what you have in mind. But I haven't thought about combining these ideas with what we try to do here.
Because like this is like the Caragiannis relaxation kind of thing on the area fixing the number of
that's an interesting question whether we can extend the results this way.
There's no more questions. So to compensate for the open problems, we are going to give a set of puzzles to Ioannis just to have zero sum.